So welcome everyone to lecture, I think it's 6, right? No, it's probably lecture 6. I think today we're going to cover something very interesting. And I didn't plan for it, but I think we kind of added it last minute. So last time we looked at how we train deep learning models. We spoke about back propagation. We spoke about hyperparameter tuning. We also spoke about embeddings and cosine similarity. This was a new topic last time as well. We went through a whole, set of examples. We looked at recommender system as a use case for for embeddings, right? And then we also, if you remember, we spoke about what are the two kinds of two main approaches in recommender systems that we spoke last time. You guys remember? Just to recap. Yeah, before semantic search, we spoke about a couple of ways to. Share with your friends. One is collaborative filtering, right?
Something related with content.
Right. Collaborative filtering and content-based filtering, right? So what is collaborative filtering? It uses user behavior or signals from there. Like if my friend watched a movie and we have similar tastes, maybe I will also like that movie. So recommend that movie to myself, right? Or recommend the movie I like to my friends, whichever way. So that's collaborative. It's collaborative in nature. You collaborate with your friends to make it happen. Then we have content-based filtering. What is content-based filtering?
You don't need that user.
You need content of the things that you want to recommend. You need to understand the movie. What's an example that we looked at last time that can help us understand a movie in a concise mathematical way? Yeah, but how do you structure the information? Embeddings. So the way to capture content is through vectors. Have you guys heard of vector search, vectorization in the context of AI? It's all coming from here. It's all coming from embeddings, because embeddings are represented as vectors, column vectors typically. So you need, if you say vector search, that means you're searching for that. Have you guys heard of RAG models? What are RAG models doing? They're doing vector search, right? Because if you ask a question to a chatbot that's using a RAG, it say, hey, can you like help me understand reinforcement learning, but use this book as a source, okay? Don't just tell me in like from your broad knowledge base, but use this specific book as a source to help me understand what reinforcement learning is. What is vector search going to help? What's vector search going to do in that case? Yeah.
It's going to query the vectors in that book.
How is it going to query the vectors in that book? But how does it get those vectors? So, yeah, but what's a vector in a book? Okay, I have a book of 300 pages. What are the vectors and what do they represent?
Different chunks.
Different chunks. How do you define a chunk?
Part of subset of what is there.
A subset of what is there in the book. Can you define a subset? Is that like 20 pages, 30 pages? What is that?
Topic.
Each topic. So it could be some, there could be some, it could also be defined by a token limit. Okay, you look at like 100 tokens at a time as a chunk. It could also be a page. Look at one page, right? One page could have roughly 200 tokens or whatever. So that piece of information goes into a vector, right? And what is a vector dimension? Yeah. Number of rows and columns.
Depends on the dimensionality, like the features that describe that.
Depends on the dimensionality. It depends on the vectorizer that you're using, right? If I use a vectorizer from, I don't know, OpenAI, it might give you like this dimensional embedding. So the dimension is fixed once you pick a vectorizer. Does it make sense? Like if I have like a 128 dimensional, so so the dimension of a vector depends on the vectorizer you're using. Have you guys taken a look at your mini project? Yeah. Did you look at the dimension of the vectors there? What are the dimensions that you saw? What is the size? 50. But you didn't have too many choices, right? It was either 50 or 25, and then there was 100 that didn't seem to work, right? It was one of those, right?
Or better, work with a specific number of words. I don't remember how many, but.
Yeah.
It's a very specific amount.
Yeah. So there is a specific number of words, but the dimension of a vector is the dimension of the embedding, right? You can take a long sentence and fit it into 50 dimensions, or you could take one word and still fit it into 50 dimensions. So the dimension of a vector captures the number of elements needed to concisely represent the information contained in that object. And that object could be a sentence or word or paragraph or a whole page of a book. Does that make sense? So it depends on your vectorizer, right? So your vectorizer determines the dimension of the vector, right? So in this case, let's say this is 50 dimensions. That 50 dimensions is decided by your vectorizer. You're using a glove embedding with 50 dimensions because it already has a model to take a word and convert it into 50 dimensions. And you're just pulling that out. That's all you're doing right now. If you retrain that model, you might still retrain it with 50 dimensions. You'll get a new vectorizer. They'll again take a word and put it into 50 dimensions. But this might be a new set of 50 dimensional elements, right? Because you have a new model. Okay, so typically the dimension of the vector that you get out of a vectorizer is fixed. It's like 128, 50, 100, 256. The more dimensions you have, the more information you can capture about that object, right? But typically for most practical tasks of semantic search and embeddings-based search, people have found that 128, 256 dimensions, sometimes even up to 1,000 dimensions is sufficient. You don't have to go into like millions of dimensions or hundreds of thousands of dimensions, right? So 1,000 dimensions is sufficient to capture information about an object. Okay, so content-based filtering is the idea of capturing and understanding content through vectors and then doing search through vectors. So you do vector search by comparing vectors. So we spoke about this last time. What's a way to compare vectors? Cosine similarity. That's one way. You could also do Euclidean distance, right? You can measure the Euclidean distance, or you can even do L1 distance. There could be other ones, but cosine similarity is very popular for these tasks because it doesn't worry about the length of the vector. It only worries about the angle. It says, so for your application, if only the angle matters, like you're in the same direction, you must be very similar. You're orthogonal, you must be dissimilar, right? If that's the thing that matters, then cosine similarity is perfect. But if you also care about the dimension of the vector, like how far, how long is it, and how short it is, then maybe you need to use a distance. Okay, so we said that. Okay, let's kind of put it together. Maybe I'll just create a new page. Okay. So basic idea is like you have objects, right? What are the objects you can have? You can have words, you can have sentences, you could have movies, you could have books. And typically books, the fine detail is it might be chunks of the book, right? And these chunks could be things like pages of a book. So like each page could be an object. So you need to define an object. Making a book an object means you might have a lot of books. And then you'll have to understand how are you going to compress a book's worth of information into a vector. So that's a separate process. How are you going to do that, right? Are you going to average it across pages and then get the vector for a book? That's a design choice that we make. But you have to first define what your objects are. Are they words? Are they sentences? What is it, right? So these are the objects. Then you have a vectorizer. So the vectorizer takes these objects and then maps them into vectors, right? So you could have like a glove vectorizer. You could have OpenAI embedding. This could be the one. You could have other ones. Maybe sentence transformer. So we're looking at sentence transformer and glove in your right in your mini project. So these would then go through, right? You might just go through this, or you might just like pass it through a sentence transformer, whichever way, right? So you pass it through and then you get a vector. So like you'd say, okay, for the word eat, I have a vector, 3 dimensions. For the sentence, I love chocolate. Again, I might have a vector in the same dimensional space. So again, this is looking at glove. If you look at OpenAI, then you might get a different dimensional embedding, right? Then we have, after this, we have semantic search. Also, you hear vector search. And so obviously, once you take objects, you vectorize it using a vectorizer. Let me just close this tab. Might increase the screen space. Then, okay, it's better. Right. So you define your objects that you care about for your application. It could be words, sentences, books, pages, movies, etc., etc. What do you want to understand? What do you want to search through? You define objects. Then you define the vectorizer you're going to use. Is it glove? Is it sentence transform? Is it OpenAI? And they have their pros and cons, right? And you understand that, okay, these are the vectorizers. This is how they are trained. We understand them. Then we get vectors, right? Now these vectors need to be stored somewhere. So what do you do for storage? Yeah. So there are different types of databases, right? What are different types of databases? Like 2 or 3 different ones that you can think of? Relational database, that's one. Like high level. SQL. SQL or NoSQL, yes. And there's also vector databases that are very good for vector storage. Relational databases are good for relational understanding, more tabular format, right? But they may not be very good for vector search. So then you pick a vector database. What would be a vector database that that you've come across? There's many of them. So there's Pinecone. You could do column storage. You could do all kinds of vector-based databases, right? So you would store these vectors. Of this. Yeah, so you store it in vector DB. So you might have heard of video DB, whatever, this DB, that DB. It's kind of a way to store specific objects in a format that's suitable for them. So you would have and vector DB is like a more generalized version of that. So you'd store vectors in a vector DB, and then once you store them and you keep it, at a time when you need to query, you'll again access the vector DB, right? So for you to go from, I'm going to pause. All right. So we spoke about objects. We spoke about having a vectorizer. We spoke about vectors. We spoke about storing the vectors in a vector DB. And we also spoke about retrieval, right? So this is retrieval of vectors for a vector search problem. And we also spoke about vector search as well last time. We said, like, if you have like a reference sentence or something, and then you have like candidates. Sorry. Anything's going on. So you have a reference sentence and you have like candidates. Sorry, can I ask everyone to pay attention here? Like there's some background noise going on. So these are candidates, like you could have like words, or you could have pages of a book, or whatever. You could have like categories. The candidates could be anything that you care about in terms of a search and retrieval. And then you match each sentence with one of the candidates. And then you get a score, maybe using cosine similarity. Then you rank it, right, from highest to lowest. And then maybe you'll pick the top one, or maybe you'll pick the top three, just so that you have some diversity. And then you'll return that as a result. Say maybe, here's what I found as like 3 different pages from a book for the question you asked on reinforcement learning. You might find one of these 3 useful. Yeah. Maybe the top one is most useful, but you never know. Like I might be looking for some variation. So including some variation, that's why we say top K retrieval, is so that you have some variety or diversity in the results as well. Okay. So this is also connected to retrieval and ranking. So here's a question for you guys. I do some vector search. I want to retrieve pages of a book that are relevant to a question I asked. Now I get like 5 different results. Or let's say I get 50 results. How do I rank these 50? And what's an algorithm I would use to do that? I have like 50 scores, 0.8, 0.9, negative 0.5, 0.2, 0.3. And then it's kind of all in different order. What do I do? But I want to get the top 3 or top 5, let's say. What's an easy way to get there? Use a heap. That's a good data structure based solution, is put it into a heap and then start popping one at a time until you get to 5. Max heap. Yeah, max heap. So we're not going too much into data structures, but the idea is that there is efficient ways to get the top 5 pages from 50 candidate pages using one of the algorithms. Like you could use a heap, you could even do sorting, less efficient, unless you want to get the top 10, top 15, then you might want to sort, right? If you just want to get the max or the best, just take the max. That's order n. If you want to get the top 5 or top, I don't know, top 3, whatever, a small number, then do a heap. If you want to be able to retrieve more, then just sort the list. And they have different computational complexity, right? One is order n, the other is order n log n. Okay, so retrieval and ranking. Okay, cool. Right. So we spoke about this last time: backpropagation, hyperparameter tuning, embeddings and cosine similarity, movie recommendations, cold start, and content-based recommendations. We also went through a quick demo web app that, given a sentence, it looks at categories that are the most relevant and then surfaces one of them. So that's doing a max retrieval. It's looking at the best score and just returning one result, right? And we saw that it was doing an okay job. It's not doing a bad job, but it's not doing a great job either. And why is that? Yeah.
The averaging.
Yes.
Does it take into account the order of the
It doesn't
words?
take into account the order of the words, right? And what is an example we discussed? Yeah. This is very important, guys. I think this is where you start thinking in terms of how these embeddings and vectors help you with search, right? So we said that if you had chocolate milk, it would have the exact same average as milk chocolate, right? If this is chocolate and this is milk, and then you say this is milk, this is chocolate, they're the same vectors, right? You just swap the order, but for the averaging, it didn't matter. So milk chocolate will have the same embedding as chocolate milk. But do we want it to have the same embedding? No. If you care about it being a chocolate or a milk, then this will not tell you that. It'll tell you it has both, right? So we said that ordering matters. Also, the quality of the embedding, like glove embeddings is based on a certain model versus OpenAI is based on a different model. So that also matters. So one is ordering that helps. The other is the quality of the embeddings that you're referencing. Like sentence transform would have a different embedding quality overall as compared to glove embeddings. So it's a combination of things that determine if your search, semantic search is accurate or not. Yeah. Okay. So today's lecture, we'll do a quick recap of embeddings and cosine similarity, and we'll be a little bit hands-on. I want you guys to be comfortable with the math as much as with the coding, as much as with the concepts. It's going to be like, we're going to be circling between these three dimensions of this class, right? And we'll look at some of the theory behind glove embeddings. How exactly are glove embeddings trained? And then we'll also do an in-class coding exercise. I think we'll have some time. We'll see how much time we have left. Okay, so before that, I'm going to disrupt the lecture because DeepSeek disrupted the LLM market today. And as you might have seen, this is from today, Jan 27th. Yesterday, it closed at 142.62 NVIDIA. And today, it dipped to 118 or something. So I would love to hear from you guys. Why did it dip so much? Yeah.
DeepSeek's saying that they trained their whole model on basically $6 million worth of NVIDIA H800 AI hours, which weren't even supposed to be relevant for AI training, which is like probably 1/1000th or even less than what OpenAI and others are claiming that they use for their training. Now there's contention over whether they actually trained it on that, but that's the claim, that it's like 1/1000th of the hardware. So for everyone trying to train these frontier models, basically DeepSeek is telling everyone we don't need nearly as many NVIDIA GPUs as we thought to train models.
Yeah. Do you guys get that? It's a low budget, high performant alternative to what's on the market, and that's scary, right? Okay. Yes.
I mean, usually it's right? So like, oh, things are getting really expensive. Things are kind of impressive, but not quite impressive enough. Oh wait, we can even solve harder problems and do more.
Yeah.
So then this might just be a short-term market reaction because
Yeah.
AI is a mystery, and so the people, Wall Street's just like, okay, we got to wait for things to kind of smooth out and
Yep.
see what people say. So
Yeah.
usually this just means, oh, we can do more now.
Yeah. Yeah. I mean, there's always a hype around NVIDIA, positive or negative. Some positive news and the stock price shoots up. So don't be surprised if some negative news and stock price goes down. So it might just be a short-term market reaction. Anything else? Yeah.
They open source the
Yes, that's a big one. That's a big one. Open source. So the code, the model, the weights, you can actually go take a look at the weights. Can you go look at the OpenAI weights? No, it's proprietary. Yeah.
Yeah, like you said, maybe makes its foundation models more accessible.
Yeah.
So then it just sort of really potentially opens the floodgates to all of them sort of community.
Yeah.
So more companies can start to like take advantage of the application of this stuff versus you have to have that pocket to get you started.
Yep. Absolutely. So anyway, I mean, there may be some hype to this because NVIDIA is not going to go away anywhere anytime soon. But it's just that it's very, very surprising that this is something that didn't happen earlier and it's happened today. And so it's kind of sending some shockwaves in the community, right? Maybe you need to rethink from scratch how you want to build foundation models and how you want to repackage things. Is more better or is less and high quality better, right? People have been training on trillions of parameters with hundreds of millions of data points and hundreds of millions of dollars in training a foundation model when you could just do it for $6 million, which is also pretty high for training a model, but it's not hundreds of millions of dollars, right? So that's probably like sending some shock waves and people are really thinking, and it's good. It's good for the AI world because you know, if you think about it, even our human brain is so sophisticated and powerful. Like if you give a new kind of a problem, reasoning problem, or there was a goat and a man and a mom and someone else standing on one end of the bridge and they had to cross this bridge, but only one can go at a time. What's the way to solve this problem? And then you break your head and you say, oh, okay, I got it. And we would reason, but it's not like we would take forever and lots and lots of data before we get it, right? We just kind of get it quickly. So but obviously we are a different system. We're a human, we're a biological system. And there is consciousness and other things that's X factor to our human body. But the idea of abstracting the neural network from our brain to artificial neural networks, that's still similar. So if we don't need so many examples to reason and understand, does AI need so many examples and so much of data? You know, that's kind of the new paradigm shift that's kind of probably coming in. Yeah.
It's a little bit like the AI equivalent of like the Greeks versus the Persians, with like the Greeks have just like a few hundred soldiers and the Persians have like a million.
Yeah.
But then, you know,
Yeah.
for one reason or another,
Yeah.
the Greeks are able to win.
Yeah. We've kind of honed in on the transformer architecture and said, this is how we're going to do it. Just go all out, throw a lot of data. But we haven't looked into the architecture. One other thing that they did is they also used reinforcement learning for training as compared to supervised fine-tuning. So this is also kind of a new paradigm shift in the way the foundation models get trained. So we'll cover supervised fine-tuning and reinforcement learning at some point, not this lecture, but supervised fine-tuning has been like the bread and butter for foundation models. And you have a loss function, and then you throw in a millions of data points, and then it takes a few weeks to train, and then it hopefully does a good job based on that data. But reinforcement learning is a different paradigm where you look at long-term expected reward and you optimize for that reward. And it's based on actions and agents, and then policies and rewards. So it has a different construct, different model. So that's something that they did, which hasn't been done before for a foundation model. So that's also new.
Question that's,
Yeah.
I don't know if that's a straightforward answer, but do you think that DeepSeek's approach, are they leveraging a lot of like what OpenAI and others have done to do it in a more efficient way? Or is it kind of, they're doing it their own way?
I think it's both. If you look at some of the DeepSeek's, sorry, I'm getting some background noise. If we can keep conversations to a minimum, just because you guys are very close to me. So I'm just getting some. So if you look at the DeepSeek's history, right, they have been optimizing, they've been using all kinds of optimizations to improve their models, but they also made some fundamental strides based on their most recent technical report, the DeepSeek V3 version that got released this year. That you can see that there's some fundamental changes that they brought in there as well. But no other company or no other project has been able to do it in $6 million. So that's for sure. There is something definitely foundational or new in the work that's done here. Anyway, yeah.
But I think the $6 million is only for the RL stage, is not for the pre-training stage. Because for my field, I saw the technical report. They do the pre-training to get the DeepSeek R1 model and R1 base model, and they do the RL training for get the R10 model. And after this, they do like some high quality data, supervised fine tuning for get the DeepSeek R1 model, and that's how they compare to like O1 model or the model.
Yeah, that's possible. It's possible. But I feel like they've used reinforcement learning to a greater extent than any other models that have come up so far. That's kind of like the fundamental difference.
There's contention too on whether the 6 million, or like, I think they did $3 million of GPU hours times $2 per GPU hour. There's contention over whether that's even accurate.
Yeah. Yeah. But it's kind of like, also, if you think about it, it's one of the only open source models that's competing with O1 right now, right? So that's definitely new. Any questions or thoughts? Yeah.
like with reinforcement learning, how does that work with backprop? I mean, is it doing like,
So there is like just like we have regular gradients in supervised fine tuning, we have like policy gradients. So they have a policy which is a probabilistic function that can predict the next action to take, which is like, how do you change the parameters or whatever. So that's a probabilistic function. So it's kind of similar, but instead of using a regular loss function, you have a policy function and you have a policy gradient. So there is definitely gradient-based fine tuning of the weights. So that's definitely similar.
What's the strategy behind like open sourcing everything? Because OpenAI doesn't do that, but these guys just.
Yeah, that's a good question. Any thoughts on that? What's the strategy to open source the weights and code and everything? Pretty much everything. And it's also MIT license. So you can do research on it and you can also commercialize any fine tunes that you do on what they've released.
Can I postulate on that one?
Sure.
I think it goes up level. There's like the huge geopolitical conflict basically between the US and China. I think it's relevant to that. I mean, by open sourcing it, the takeaway for me is like Trump last week said we're going to invest $500 billion on AI. And then this week, China said with $6 million, we did more than you've done. So I feel like on the one hand,
Okay.
there's like the company aspect, but then there's really like the geopolitical
Okay.
aspect.
Okay, we'll leave the political aspect aside for this class, right? But it's a fair point, but I don't know. I don't think I want to dwell into that for this class. But yeah, so it's a good one. Yeah, you had some thought?
I mean, there's been plenty of open sourcing that's happened before this moment. More people contribute, it ups the bar more and more and more.
Yeah.
So, I mean, from a corporate perspective, Elon is famous for saying, hey, here's all our copyrights, here you go, use them all. And
Yeah.
That just allowed his company to have a larger ecosystem. Had the opposite effect.
So what I feel is they've released something, but they have more in the pipeline that they haven't shared yet. So that's how it works. There's more coming out. So by the time you catch up, they're already like, ahead on the game. But it's good for the community to open source it.
Came up with something. What I was reading today was that there was a mentality that people had that if you want to train a better model, you need more compute.
Mhm.
Now, because what they have done, do you think there's going to be a shift in the way people perceive making better models? So it will be more optimization than compute. Do you think that would happen?
It's hard to say, there's been a lot of research on small, medium, and large language models. So that's always been going on. And there's also, even with the R1 model, they've released like distilled versions that are like you have 8 billion parameters and then you have 32 billion parameters and then and so on, right? So it goes to 80 billion and so on. And so it's definitely a fact. I mean, if you look at the 8 billion, it's definitely a factor of 100 fewer or 100x fewer parameters. But it has a less performance than like a 32 billion model. But between like 32 billion and maybe 64 billion, there's not much gap. So there is some sweet spot on how many parameters you should have to match up to an accuracy. It kind of flattens out like that. So you'll have to still work on that. I don't think we're there yet that you can just kind of make it really small and then say we're done. But definitely will make a lot of people think about optimizing and doing more with less, right? Because cost is a big concern for a lot of people. Yeah, so it's a very fascinating discussion. And I think this graph brought everyone's attention to DeepSeek. Anyway, so okay, so we kind of focused on DeepSeek and how it's disrupting the market, and discuss some of these. It's low budget. There's some hype. it's open source and it relies more on reinforcement learning than other models. Going back to last class, I think it's good if we all get hands-on with some of the computations here. So I would love for you guys to again work in groups of 2 or 3. Just take a look at this problem. Let's consider 3-dimensional embeddings for now for movies. Let's say we had 3 movies: Avatar, Iron Man, and Rain Man. So given that you like the movie Avatar, which movie would be good to recommend between Iron Man and Rain Man, and why? So I use the concept of embeddings and cosine similarity to derive your result. So basically, this is Avatar's vector, this is Iron Man's vector, and this is Rain Man's vector. So given that you have these vectors, which would you prefer between Rain Man and Iron Man as a recommendation for this user? Okay. So maybe take like 5 minutes and you can just work in groups and we'll catch up. Okay, maybe we can get started. So what's your answer? Iron Man, Rain Man? Iron Man? Okay. Let's just go through the math just to make sure. So E1 is 122. E2 is 378. So this is like a 3-dimensional, right? All of these are 3 dimensions. 1, -2, 6. So this is Avatar, this is Iron Man, this is Rain Man. So the cosine similarity between E1, E2 is E1 dot E2 divided by E1, E2, right? I think it's good to compute E1, the value of this thing is 1 plus 4 plus 4. This is the norm of E1, so that's square root 17. E2 is 9 plus 49 plus 64. There is something, I don't know what it is. 113, 122. And then the norm of E2 is 1 squared plus -2 squared plus 6 squared. So that is equal to 41. Yeah. Okay. So now that we have these things, we just have to compute the dot product. So what's the dot product of E1, E2? $34?
33.
33? Yeah, 33. That's right. Okay, so that's 33 divided by square root 17 square root 122. And then the cosine similarity between E1 and E3, right? So we need to take, we're comparing Avatar and Iron Man, and then now we're comparing Avatar and Rain Man, right? So what's the dot product of E1, E3? So that's, is it 15? So this is 1 times 1 minus 2 times 2 plus 6 times 2. So that's 9, right? So you have to take the sign into account here. So for the norm, the sign doesn't matter because you're squaring it. But for the dot product, the sign matters. Okay. So this is equal to 13 divided by, or sorry, not, is it 13? 12, 13, 11. So this is 11. Okay. This is equal to 11 divided by square root 17 and square root 41. Okay. So which is bigger? Is the numerator 9? 13 minus 4, 9. You're right. Right. Okay. Which one's bigger? Yeah.
The top one.
This is bigger, right? Yeah, that makes sense. Because it's kind of 4, the numerator is 4 times bigger, but the denominator is not 4 times bigger. It's kind of, yeah. Is that right? I don't know. You guys tell me. That's right. Okay, so that's what we would kind of say is the cosine similarity of E1, E2 is bigger than cosine similarity of E1, E3. So I would predict Iron Man as a good recommendation for Avatar.
So you want the cosine similarity to be larger.
Larger, right? Does it make sense? Any similarity metric is based on it being larger. Any distance metric is based on it being smaller. Yeah. Smaller is better for a distance metric. Larger is better for a similarity metric. And similarity is kind of like just the reverse of distance. Is loss function when we do training of machine learning model, is that a distance metric or a similarity metric? It's a distance metric, right? Because you want the loss to be small. The smaller the loss, the better. Otherwise, your loss is higher. So it's kind of self-explanatory. So loss is actually a distance metric because it's a distance between the prediction and the truth. That's the loss. How far is the prediction for any example on an average from the truth for any example on an average? That's the loss function, right? Cross entropy, that's a loss function. Euclidean distance, that's a loss function, right? Triplet loss, you might have heard about it. That's another loss function. So these are all distance metrics. So when you look at that, you first ask, is it a distance metric or is it a similarity metric? If it's distance, smaller the better. If it's similarity, higher the better. Okay. So cosine similarity, we want it to be, what's that?
Also plotted them
Oh, you also plotted it. Amazing.
to see so they're extreme.
Yeah, okay, maybe we should show it. Yeah, I don't know if you can see, but what's your name?
Najib.
Najib plotted the vectors, so you can see the Iron Man and Avatar are very close to each other. Visually, this is how it is in 3 dimensions. But you cannot visualize this in 100 dimensions. But you can compute the similarity in 100 dimensions. So that's the benefit of computation. Okay, cool. Okay, so the visual makes intuitive sense of what the math you just computed. Okay, cool. All right, let's, I think before we go here, we should probably talk about the project teams. If you want to come up.